All right, Matt 2, here we go. We got 7.1.5, using similar triangles to prove theorems. All right, the first thing we're going to prove is the triangle midsegment theorem. Okay, so a midsegment is a segment that connects two midpoints of the triangle. So the two midpoints are D and E. So the midsegment must be segment DE. Okay, what appears to be true about this midsegment? Well, the two things that are true, and what appears to be true, is definitely that these two are parallel. So the midsegment is parallel to the base of that triangle. So we know that for sure. Well, not for sure, we're going to prove it. And then it also looks like the midsegment is about half the size of AB. So we're going to prove that as well. That basically that AB is two of those midsegments. So basically, DE is half the size of this other one. Okay, what we're going to do is we're going to use triangle similarity to prove that. So in order to prove this, we need to show that these two triangles are similar to each other. So we've got a reflexive angle up there, because on the small triangle, angle C is one of its angles, and then on the big triangle, angle C is one of the angles. So we know that angle C from the small triangle is congruent to angle C from the big triangle, and that's the reflexive property. Then if you look at it, this side here from the small triangle corresponds to this big side from the big one, and you see here that this is equal to this. So that means that the small triangle is half of the big triangle over there, because this segment and this segment are the same length, because they're congruent to each other. So the small segment, that's 2 to make up this big segment over here. And we're just going to say that we know that CD is equal to CD, because that's given, because of the midpoint right there. And then we also know that AC is equal to CD plus DA. So CA is equal to these two parts made up of each other. And then what we can do is we can use substitution and plug in CD over into here, into DA. So for this we used given and segment addition. We'll just write segment addition. So the next step over here is I can say that AC is equal to CD, AC is equal to CD plus CD, because we're substituting in here. Oh, this looks really bad, sorry. AC equals, which basically means that AC, gosh, I did it again. AC is equal to 2 of the CDs. And we just use substitution there. We did it with one side of the triangle. We can do the exact same thing to the other side of the triangle. Oh man, I did it again. This was supposed to be an A. This is what I get for rushing. All right, so over here, I see that CE is equal to EB. And I see that CB, that entire segment there, is equal to 2 separate segments added together. So that would be CE and EB. And again, what we're going to do is instead of EB over there, we're going to plug in, oh, I messed it up here. This is supposed to be an A. And that's still supposed to be a D. Wow, I really screwed that side up. Anyways, we're going to substitute over there. So segment addition for that one. Then we're going to say, okay, so instead of EB, we're allowed to write CE. So we can write that CB is equal to CE plus CE, which is CB equal to 2 of those CEs. Same reasons that we had here. And now what we have is these two sides are proportional in a ratio of 1 to 2. And these sides have the same ratio, the ratio of 1 to 2. So they have the same scale factor. So by side angle side, those two are similar to each other. So we can say that triangle CDE is similar to triangle CAB. We showed that the two sides were in the same scale factor, or the same ratio of 1 to 2, 1 to 2, and then the reflexive side in between. So SAS similarity. Okay, now that we know that they're similar, remember when they're similar that the corresponding angles are congruent to each other. So I'm going to say from here that this angle up here corresponds to this angle down there. And so they have to be congruent to each other because we just proved those two triangles were congruent. So I'm going to say that angle A is congruent to angle CDE. And that's because of corresponding angles are congruent in these triangles. And then I can now say that DE is parallel to AB because these are corresponding angles, and when corresponding angles are congruent, the lines have to be parallel. So corresponding angles congruent, that means that we have parallel lines. So I've just proven that they're parallel because that's what the mid-segment theorem says. It says that those two are parallel. The other thing that the mid-segment theorem says is that AB should be half of DE. And we can prove that just in one step. AB has to be half of DE because we said that they're similar. So all three of these sides have to have the same scale factor. Here we said that the ratio is 1 to 2. Here we said the ratio is 1 to 2. So the last side also has to have a ratio of 1 to 2. So sides of similar triangles have the same ratio. So there you go. We proved that the mid-segment theorem works, that the mid-segment is parallel and half the length of the base there. Okay, now we're going to prove the Pythagorean theorem using these three triangles here. We've actually got three triangles. We've got the big triangle, we've got this medium triangle over here, and I've got a small triangle over there. These three triangles are all similar to each other. Because let's look at the big triangle. The big triangle has a 90-degree angle, it has this angle, and then it has this angle over there. Now, if I'm looking at this triangle over here on the left, we'll call this the left triangle. We'll call this one the right triangle. And then we'll call the whole thing the big triangle. Just, there you go. So the left triangle has a 90-degree angle here because we've got linear pairs, and then both of these have to be 90. And so since we've got angle, the big triangle has 90 degrees and 1 tick mark angle. The left triangle has 90 degrees and 1 tick mark angle. So that means that they're similar to each other by angle. Now, if two of the angles are the same, the third angle also has to be the same. So looking at the big triangle, the third angle we put over here is 2 tick marks. So the third angle of this triangle has to be 2 tick marks for the left triangle here. 1 tick mark, 2 tick mark, 90. Big triangle has 1 tick mark, 2 tick mark, 90 for that big one up there. The triangle on the right and the big triangle are also similar to each other because the triangle on the right has 90 degrees and 2 tick marks. And the big triangle has 90 degrees and 2 tick marks. So that means that this last angle for the right triangle has to be 1 tick mark because if two of the angles are the same, then the third angle also has to be the same. So those are the three triangles that are congruent. The big triangle, the left triangle, not congruent, similar. The big triangle, the left triangle, and the right triangle. They are all similar to each other. Okay, so now we're going to say that DB is this part from the left triangle. So that's from the left. AB is from the big triangle. And then AB, wait, did I, oh, dang it. No, DB is from the right triangle. Sorry. Okay, sorry. DB is from the right triangle. And DB is between 9 degrees and 2 tick marks. AB from the big triangle, this is the big triangle. Jeez, I'm really messing stuff up today. Sorry, I'm in a rush. All right, so DB is from the right triangle, and it corresponds to AB from the big triangle, because DB is between 90 and 2 tick marks, and then over here, 90, 2 tick marks. So those two correspond. AB from the right triangle, AB is right here. It's between 1 tick mark and 2 tick marks. And from the big triangle, that corresponds to AC. No, dang it, CB. It corresponds to CB from the big triangle because we got 1 tick mark and 2 tick marks. Okay, I'm going to get this right eventually. DC, that's from the left triangle. DC is 90 and 1 tick mark. Now, if we compare it to the big triangle, AC from the big triangle is between 90 degrees and 1 tick mark. So those two correspond to each other. AC from the left triangle is between 2 tick marks and 1 tick mark. And then BC from the big triangle is between 1 tick mark and 2 tick marks. So we can set up those proportions because they're corresponding parts. These two compare the right triangle to the big triangle. These two compare the left triangle to the big triangle. And we're going to use this cross products to see if we can prove the Pythagorean theorem works. So cross products, this would be AB times AB, that would be AB squared, is equal to DB times CB. So I'm just using cross products, AB times AB, DB times CB. We'll do the same thing on the other one, AC times AC, that's AC squared, is equal to DC times BC. All right, now we're going to add the equations together. So an equation says that this side's equal to this side. So what I can do is I can take this and add it to this side. And then I can take this and add it to the other side. So since they're equal to each other, I can add 1 to one side and 1 to the other side. And what are we left with when we do that? We are left with AB squared plus AC squared equals DB times CB plus DC times BC. All right, I'm going to move so the lights don't turn off. All right, I've moved around. Our lights aren't going to turn off. Good. All right, next step. We're going to rewrite the right-hand side by factoring. See how they both have BC in them? So I'm going to rewrite that side. So the left side is going to stay the same. On this side, they both have BC, so I'm going to factor out BC. And then I'm left with a DB plus a DC. I guess I didn't need the parentheses there. So I factored out BC. BC is right here, BC is right here, so I got BC here. All right, now looking at our original part here, it says DB plus DC, that's DP plus DC. DB and DC together make CB. So instead of this, I can rewrite it This is still BC. So dB plus DC here, dB plus DC, together they make BC. So what do I have? I've got AB squared plus AC squared equals BC squared. Now, if you look at our big triangle, that would be this side plus this side squared plus this side squared equals the hypotenuse squared. That's the Pythagorean theorem. We just proved that it works using similar triangles. All right, backside. Almost done. All right, so Sophia lays coordinate grid on a graph paper. She's looking at an astronomical star chart. So she knows that star A is located at -4, 2. And star B is located at 8, 4. All right, so star A, we're going to put over here at -4, -2. There's star A. And star B, we're going to put up at 8, 4. All right, there's star B at 8, 4. All right, there's an asteroid that's located between those two stars, directly in between them, where the midpoint is. So you can use your midpoint formula, where the midpoint formula says that you just add these two numbers and divide by 2. So if I took -4 plus 8 for the x's and divide by 2, and then took your y values of -2 plus 4 and divided by 2, you would find out that the midpoint, where the asteroid should be, would be 4 over 2, which is 2, and then 2 over 2, which is 1. So that's one way you can do it. You can do it algebraically. And that looks like that's right in the middle. So there's the asteroid. You can also just look at the slope. This one goes up 6 and over 12. So instead of going up 6 over 12, you can go half of that distance of up 3 and over 6 and get to that same point. The other thing we want to know is how far is this distance from star A to the asteroid? Well, we can make a slope triangle right here. Since this is 3 and this is 6, we can just do 3 squared plus 6 squared equals that distance squared. Or we can just take the square root of 3 squared plus 6 squared. Pythagorean theorem or the distance formula like this. Either way you do it, you get 9 plus 36, which is the square root of 45. So it's getting close to 7. It's 6 point something. Root 49 would be 7. So this is getting close up to there. So 7 point, I don't know, 7.7 or 6.7, somewhere like that, maybe. Sophie's modeling the path of the comet as it flies through the galaxy. If she assumes the comet is flying in a linear path, so in a straight line, what are the coordinates of the comet when it is 1/3 of the way from A to B? All right, so 1/3 of the way should show up somewhere around in here, right? So what we can do for that is we can look at the x's and the y's individually. The x's start at -4. And then if I want to go plus 1/3 of the way from -4 to +8, how much of a change is that going to be if I go from -4 to +8? -4 to +8 is a change of 12. Well, I want only 1/3 of that change. So this is -4 plus 4. So the x value should be 0 for 1/3 of the way. And then we do the same thing for the y value. We'd say, okay, the y value is starting at -2. And then I want to go 1/3 of the way of the change in the y value. The y value going from -2 to +4 is changing by 6. So I'm going to do 1/3 of 6. So we would end up with -2, 1/3 of 6 is +2, which would be 0. So it looks like 0, 0 is 1/3 of the way there. And 0, 0 is straight on this line. So yeah, that kind of makes sense. It looks like about 1/3 of the way. We could check it by going up 2 over 4, up 2 over 4, up 2 over 4. And yeah, that's 1/3 of the way there. And we do the same thing for 3/4. So for 3/4, we'd say, okay, we're starting at -4. We want to go 3/4 of the way of the change in x, which is 12. So -4, 4 goes in 12 3 times. 3 times 3 is 9, so plus 9. So the x coordinate would be 5. And then we need to find the y coordinate. We're starting at -2. We want to go 3/4 of the way. The change in the y value is 6 because it's going from -2 up to 4. So times 6. So this is -2. This is 18/4, which reduces to 9/2. And 9/2 is 4.5. So 4.5 minus 2 is 2.5. So our point should be at 5, 2.5. Let's see if it's on this line. We're going to go 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5, 1, 2.5. And yeah, that looks like that is along those lines here. Here was 1/3 of the way, and this looks like this is 3/4 of the way. And finally, let's do this last one. The x coordinate, we start at -4. We're going to go 2/3 of the distance. The distance going from side to side is 12. So this is -4 plus 3 goes in 12 4 times. 4 times 2 is 8. So that's +4. For the y coordinate, we're starting at -2. We want to go 2/3 of the way. The total change from the -2 to +4 is 6. So 2/3 of 6. So 2/3 of 6 is 4. So we get 2. So 4, 2 would be 2/3 of the way. So 1, 2, 3, 4, 1, 2. And yep, that looks like it's on that line since it's a linear path. All right, that's all I got for you. Math hard. See you later. Bye.